Hello, our team Fossil, and I'll be presenting our final project for the Introduction to Engineering Design course in the first semester of the 2026 academic year. Our team designed and implemented a smart library seat management system to serve the inefficient seat monopolization problem that many library users have experienced at least once. Many of you have probably experienced going to the library during exam season to study, only to turn back because there were no available seats at all. But was the library really lacking seats? In reality, when we look around the library, nearly half of the seats are occupied by so-called ghost occupancy, situation where only textbook or bags are left behind for long periods while no one is actually there. As a result, students who need a seat struggle to find one, while library staff must repeatedly walk around the large library to manually check and manage unauthorized long-term seat occupation, creating a highly inefficient system. Our team started this project with one simple question. Could we use sensor technology to automatically detect and solve situations where belongings are left behind without the actual user being present? Our objective tree was created to establish both quantitative and qualitative goals for the system we aim to design. We identified three major criteria. First, practicality. First, system to be widely implemented in real university libraries. It needed to be low cost, have a simple and reliable circuit design with fewer chances of failure, and allow ease maintenance. Second, detection of occurrence. The system needed to accurately distinguish whether an actual person was sitting at the seat or if only belongings such as bags or books had been left behind. Third, management efficiency. When unauthorized seat occupation is detected, both library staff and waiting students should be able to recognize the seat status intuitively through a simple user interface, such as LED indicators. Based on this object tree, our team began designing the optimal hardware components and control methods for the system. Next, we would like to explain the hardware concept design stage. Our team brainstormed various candidate sensors for detecting users and seat occupancy. As shown in the table, we considered ultrasonic sensors, PI sensors, and sensors for human detection. For seat occupancy detection, we analyzed pressure path, FS sensors, and mechanical switch sensors. As a result, we conclude that the optimal solution was to combine a PIR sensor, which precisely detects human movement, with an FS sensor, which sensitively measures the weight of objects using an Arduino board. For the warning system, we select a visually intuitive LED indicator instead of buzzer, considering the noisy environment of our library. Here comes the most important engineering design idea of our project. Why is a single sensor not enough? The FS sensor is an excellent tool for detecting the presence of an object. When pressure is applied, its resistance decreases, and based on the voltage divider principle, the system can determine whether an object exists. However, if only one FS sensor is used, the system may mistakenly recognize a heavy textbook or a bag as a person occupying the seat. On the other hand, the PIR sensor detects changes in infrared energy emitted by the human body through a Fresnel lens. In other words, it only responds to the movement of living being, so does not generate false alarm from objects. However, when a user sits still and concentrates on studying, the sensor may fail to detect movement and incorrectly assume that no one is present. Therefore, we designed the system so that the physical weakness of the two sensors compensate for each other perfectly. while the FS sensor continuously monitors the presence of an object. If the PIR sensor detects no human movement for a certain period of time, the system determines that the seat is occupied only by belongings without an actual user present. Based on this concept, we implemented a sensor fusion algorithm for detecting unauthorized seat occupation. To objectively evaluate the various sensor combination alternative we designed, we created a decision matrix based on several evaluation criteria. The systems were evaluated in terms of cost, usability, accuracy, and field suitability. The mechanical switch and PIR combination received low scores in precision and usability, while the ultrasonic sensor combination showed high possibilities of malfunction due to sensoring range limitations. In contrast, our final solution combining FS sensor and PIR sensor demonstrates the highest accuracy and excellent usability relative to cost. As a result, it achieved the highest overall score of 4.3 and was selected as the final design. Moving on, I would like to talk about the expected benefits of implementing this system. Let's first look at our current situation, the before stage. As of now, library staff must manually work around and check every single seat. This leads to a common frustration where students cannot sit at seats that are hooked just by bags. Ultimately, there is no way for anyone to know the seat status in real time. However, after introducing our system, the after stage brings a complete transformation. First, the system features auto detection and an LED alert system. This ensures that unoccupied or violated seats are redistributed quickly to waiting students. Most importantly, the workload for our library staff will be dramatically reduced. To break this down further, we deliver four core values. First, higher seat turnover. The system instantly detects violations and redistributes the seats to students who are actually waiting. Second, intuitive LED alerts. Staff can see the seat status at a single glance, meaning no more unnecessary patrol runs. Third, a realistic budget. We have provided a clear and transparent total estimated cost and component breakdown to keep it cost effective. And first, it is highly expandable. This system is future-proof and can easily scale to a mobile application or centralized dashboard. In conclusion, this is a practical solution ready to deploy in a real university library. Thank you for your time. This budget plan was carefully designed with large-scale implementation in university in mind, including the Arduino board, two FSR pressure sensor, PIR sensor, LEDs, breadboards, jumper wire, and AAA battery holders for power supply. We were able to build a prototype at a cost of only about 6,400 won per seat, compared to expensive commercial thermal cameras or smart seat management system that cost hundreds of thousands of won. Our system demonstrated that a ghost occupancy detection solution with similar or even higher accuracy can be implemented at nearly one-tenth of the cost. Now we would like to explain the prototype we actually implemented and the demonstration scenario. Using black foam board, we built a model of a single person library desk. A PIR sensor was mounted on the upper wall to detect upper body movement, while an FSR pressure pad was embedded underneath the desk, meant to detect the weight of the books or laptops. Through the serial monitor, we verified that the system could perfectly distinguish three different states. The FSR resistance value is low and no motion is detected by the PIR sensor, indicating that the seat is empty. Stage 2, the state occurs immediately after a user sits down and or when belongings are placed on the desk, causing the FSR value to increase. Stage 3, pressure continues to be applied to the FSR sensor, meaning belongings are still present but no human movement is detected by the PIR sensor for the present timeout period. This indicates a ghost occupancy situation. At this moment, the Arduino board immediately turns on the warning LED to notify nearby users and library staff that the seat is being occupied without an actual user present. In conclusion, the Smart Library Seat Management System developed by our team is a successful engineering design project that intelligently overcame the limitations of single sensor systems through a multi-sensor fusion algorithm. The system can be implemented at very low cost, provides an intuitive user interface, and can be easily expanded into a centralized web-based on control system and smartphone application in the future. We believe this solution can contribute to establishing a healthier self-study culture in university libraries and to improving the efficient use of shared resources. This concludes our presentation. We are Team Force. Thank you for listening, and we would be happy to answer any questions.